Hey, dummy. Are you bad at math but still want to do cool space stuff? Maybe you're like me and thought to yourself one warm afternoon, how come I can't find a 3D map of all the stars we found with planets? Worry not, fellow math dummy, because today I'm going to show you how to design an accurate star map in 3 dimensions with the absolute bare minimum of mathematical effort. Just to be clear, there is math involved in this, but most of the work has been done for us. You'll be learning just enough of the concepts involved to help you plug the right information into the spreadsheet software of your choice. Whether it's Microsoft Excel, Google Sheets, LibreOffice Calc, or something I haven't bothered to look up. If you didn't know that spreadsheet software can do complicated trigonometry, well, you've learned something already now, haven't you? Before we continue learning, let's give a shout out to all my sponsors. If you'd like to support the channel or my podcast, AE Reads Skiffily, where I read science fiction stories and add immersive sound effects and music, head on over to my Patreon page and click Become a Patron. Patrons get exclusive access to behind-the-scenes content, community polls, and the knowledge that they're making my life just a little bit better. In mathematical terms, what we're doing today is converting from spherical coordinates to Cartesian ones. You're probably most familiar with Cartesian coordinates from graphs that have an x-axis for left and right and a y-axis for up and down. Since we're working in 3D, there's also a z-axis that represents forwards and backwards. Presumably, the sorts of calculations we're doing could work for a 4th dimension, but we don't have time for that. To understand the celestial coordinate system, imagine that the sky is a giant ball around the Earth, which is something people used to believe. Each star is located somewhere along the interior surface of this sphere. In order to designate a star's location on this interior surface, astronomers have come up with a sort of inversion of the geographic coordinate system that gets you latitude and longitude on your GPS. Just like GPS, once you know a star's celestial coordinates, you can pinpoint it in the night sky, or the day sky in the event of a bright enough supernova. However, instead of latitude and longitude, celestial coordinates are given in right ascension and declination. Right ascension is a star's location along the celestial equator. The units given are in hours, which can then be broken up into minutes, seconds, and so forth for greater precision. Declination is the celestial equivalent of latitude, with a star's location being somewhere beneath the top and the bottom. Declination is given in degrees, but it's between 90 degrees and negative 90 degrees, and then degrees are broken up into minutes and seconds. They probably did this just to make it more complicated for us dummies, but one should never underestimate the cleverness of lazy folk like us. With celestial coordinates in hand, the only other additional information we need about a star to get its XYZ Cartesian coordinates is distance, which lets us know how far away a star is from the solar system. Do I need to explain distance? The higher numbers are further away from us. The nice thing about the math in this video is that it works no matter what distance unit you choose, as long as you're consistent. So, Alpha Centauri's distance from the solar system could be 12.2 light years, or it could be 1.295 parsecs, or any other unit you want. 71.7 trillion miles, 115.4 trillion kilometers, 126.2 quadrillion football fields. That's quite a game. So the first thing that you've got to do is convert the celestial coordinates into degrees. Oh, wait, we got to get the celestial coordinates. While Cartesian XYZ coordinates are harder to come by, right ascension and declination are readily available. I'll grab the celestial coordinates for Alpha Centauri from the Internet Stellar Database. Simple enough. I've even got a link to the Internet Stellar Database in the video description. That saves you the hassle of Googling it. Now we've got to convert the right ascension and declination into degrees. Here are the equations for it. For the right ascension, you multiply the hours by 15 because 24, the number of hours in a right ascension circle, fits into 360, the number of degrees in a circle, 15 times. You multiply the minutes by 0.25 because 1,440, the number of minutes in a right ascension circle, fits into 360.25 times. Are you losing me? It doesn't matter. What matters is translating these equations into spreadsheet formula, and that's so easy, it's like Christmas. So, for Alpha Centauri, with right ascension in cell B2 over here, and declination in cell C2, we can put these equations in. Don't worry, I've got the equations in the video description for you. Take note that for declination in cell C2, I put the whole equation in parentheses so that I could reflect its negative status more easily. Otherwise, I'd have to change all the addition signs to subtraction signs or put more hyphens. If you haven't been able to figure it out, we're doing this with as little work as possible while still being able to say we did it ourselves. If the declination is not negative, or what you might call positive, then you don't need the negative sign there. Here comes the hard part. These are the equations that convert celestial coordinates into Cartesian ones. For the uninitiated, sine and cosine are trigonometric functions of angles. What they do or how they're derived doesn't matter. No one does it by hand anyway, so there's a little bit of a Chinese room thing going on here. We don't actually need to understand what these trigonometric functions represent. You just have to be able to plug them into a calculator. Here's what these same equations look like in spreadsheet format. However, spreadsheet software is weird, and for some reason assumes that angles are given in radians. Who uses radians? We don't. So we've got to modify the equations just a little bit. These are the equations' final form, so I've got them in the video description for you. These are the numbers that we get. Since the Internet Stellar Database happens to also provide Cartesian coordinates, let's compare. It's a perfect match. Now we're cooking with hydrogen. That's how you do one. Let's grab ourselves a grip of stellar data. Since 1992, more than 3,000 stars have been found to have one or more planets orbiting them. That's a lot to put in by hand, even if you're using special software, but this wouldn't be the dumb, lazy person's guide to accurate star maps if you had to manually plug in the data for every star, now would it? For step 3, we're heading on over to the Extrasolar Planets Encyclopedia. The link, say it with me, is in the video description. The Extrasolar Planets Encyclopedia, or as serious scientists call it, EP, has a CSV file that you can download and open in your spreadsheet app of choice. As you can see with these column headers, there are a lot of parameters here. We only need a few. There's our friends' right ascension and declination. You'll notice that the folks at EP have converted the celestial coordinates into the degree format that we want, which saves us a bit of work. Distance is in parsecs, which is really my preferred unit anyway. We also want to keep the star name column. And then just delete the other columns. Doing things the quick and easy way comes at a price. Many exoplanet systems have multiple stars. Our neighbor Alpha Centauri has 3. But this method doesn't allow for easily identifying or incorporating this content into the software I'm going to have you use. So, we're treating all of these systems like they have 1 star. We're just getting their 3D coordinates, not telling their life story. Some of the entries are missing content. It's easier to remove or fix each star with missing content by sorting a column and then going to the bottom and dealing with the missing data. For example, a few dozen entries don't have star names. For the purpose of this video, we're going to treat these systems as unusable. With a little bit of work, you can often find these gaps in data, but I'm not about that life. At the time that I'm making this video, which is August 2019, more than 1,000 stars don't have distance information at EP, which basically makes them useless for us. This is probably the fault of lazy astronomers, but given the glass house we're living in here, it's best not to be too critical. We've got 2,932 star systems, which is a lot when you think about it. The next order of business is to remove all the duplicate entries that come from multi-planet systems. You can see here, for example, that GJ273, or Lyton star, appears a few times because we found multiple planets orbiting that star. Removing duplicates is pretty straightforward, but the method differs depending on which program you use. If you're using Microsoft Excel, then you want to click on Data and select Remove Duplicates, which is under Data Tools, and then under Columns, leave only the star name column checked. If you're using Google Sheets, then go to Data menu and select Remove Duplicates. A dialog box pops up and gives you the option to select Column has headers. While it's true that our columns do have headers, that's not too important right now. Maybe in the future, when they name a star right ascension, we can worry about that. Anyway, select just the column with the star names, then select Remove Duplicates. If you're using Calc by LibreOffice, you should just use Google Sheets if you don't have Microsoft Excel. And you can't even do this in Microsoft Excel 2000. We've got our data just the way we want it. Now you can copy over the equations we've made into the spreadsheet with all the star information. Because spreadsheet programs use relative references, you can copy the cells into subsequent rows, and the cell references will automatically adjust. The program I'm using to map out the stars is called It's Full of Stars. The program is from 1997, so, of course, the original GeoCities link no longer works. Just in case you can't find a copy by Googling It's Full of Stars and Klaus Bernich, the guy who programmed it, I've uploaded the massive 1.6 meg zip file to Google Sites. This program works on any version of Windows with no trouble whatsoever. The main reason why we're using this program is that it's free, and the primitive save files are editable in our text editor of choice. This will allow us to easily add our thousands of star systems from our spreadsheet data. But you've got to do it in just the right way. First, we want to create an str save file in It's Full of Stars. Select Edit and then Create Solar System. You can see that there's a lot of information you can put into a star system. Some of it's quantitative, some of it is just basically text. We can put anything we want, but since our database doesn't have the solar system, we might as well just put that. You can either select Solar System Prototype or just put a name here and keep the star system coordinates as 000. Then hit Save. The file name and file location don't matter as long as you remember what you called the file and where you put it. Now, open the str file in Notepad. Each slash indicates a new entry in a star system's data. Since we can edit this as text, we can semi-automate the process. We just have to translate the information we have here to the format that the program reads. Luckily, spreadsheets can help us out with that. You see, when you copy two or more adjacent cells from a spreadsheet and paste them into a text-only program like Notepad, it will convert the cell boundary to the ASCII tab character, which is just an extra long space. Since we can do a hunt and destroy of one character with another, we can set up a spreadsheet row to position our data and cell boundaries in just the right places, then convert the tab character into properly positioned slashes. Sound complicated? Only when you think about it. The only other hurdle in this is that the entries in It's Full of Stars save files need line breaks in certain spots. To insert line breaks, what we're going to do is we're going to use the HTML line break indicator and an HTML reader. I'll walk you through the process of converting line break HTML code to actual line breaks, but first, let's format the data in the way It's Full of Stars likes. Create a new sheet in your spreadsheet file. Each row in the sheet we've created will have a corresponding entry in this new sheet that will lend itself to the It's Full of Stars format we want. In the video description, I've put a line of text that you can copy and paste into your spreadsheet software, but I'm gonna explain it a little bit. No matter what program you use, it'll automatically convert the tab character into cell boundaries. The only other things you have to change yourself are the cells for the XYZ coordinates and the cell with the star's name. It looks complicated at first, but once you get one row done correctly, you can copy the row a few thousand times, or 2,932 times, for all the other stars. All right, so you can see cell A is just an S, which stands for star. Cells B and C are blank. Cells D, E, and F, those are your XYZ coordinates. Since you've already figured these out, you can actually just use the spreadsheet software's relative references to duplicate the content. If you don't know how to do that across sheets, go into the cell you want. We're doing the x-axis value cell for our first star, Alpha Centauri. Type the equal sign and then click on the first sheet and select the x-axis cell for that star. Then press enter. Now, whatever content is in the x-axis cell for Alpha Centauri is in the first sheet that will also be in the x-axis cell in that second sheet. You can even copy the cell with the reference formatting to Y and Z, and it should, with its relative references, automatically convert to the Y and Z cells from the first sheet. For good measure, these cells should be formatted with no more than 2 decimal points, and if you're working with units small enough to give you results in the thousands, be sure to format them so that there are no comma separators. It's not going to render right if you don't do that. Formatting cells is pretty straightforward. Select Format and either select Cells in MS Excel, in Google Sheets, select Number, More Formats, and Custom Number Format, and in LibreOffice Calc. Why are you still using LibreOffice Calc? These cells, G, H, I, J, M, and N, have zeros. K is blank. O represents the Morgan-Keenan stellar type, which is associated with a star's color. If you leave it blank, it will default to red, the M-class color. There's a way to get accurate star class letters in that column pretty quickly. I'll be showing that to my Patreon supporters. If you have this information for the stars in the other sheet, you can do the same relative reference technique that I showed you with the XYZ coordinates. P represents the star's luminosity class. You can leave that blank, or you can just put 3, which represents the main sequence class. Many of these stars are main sequence stars anyway. Q is the star name. You should do the same relative reference technique that I showed you. R has 2 line breaks. S is blank. And the best way to do the rest of the cells, if you aren't going to bother just copying from the video description, is to put a 0 in every cell from T through AV, then put a single line break in AH and AY. Did you get all that? No, of course not. Like I said, you can copy and paste the line of text into your spreadsheet software. The only things you need to put in yourself are the coordinates and the star name. And really, it's going to save you a lot of effort to just do that relative references technique. Copy the rows into Notepad. You can actually copy whole rows rather than trying to copy just the right amount of columns. Next, you want to replace all the tab characters with slashes. Since hitting the tab key while you're in the search and replace dialog box will just cycle you through the dialog box's options, you'll want to copy a tab character before you go into the Find and Replace dialog box. Paste the tab in Find What and type a regular slash in Replace With. This will convert all of the tabs, which were cell boundaries in the spreadsheet, into the slashes we want. As promised, I will now show you how to convert the HTML code for line breaks into actual line breaks. Copy the text from Notepad and head on over to your favorite HTML editor. I'm using Real-Time HTML Editor. paste the text into the HTML section up top, and copy the results at the bottom. Then paste those results at the end of your str file that you've opened in Notepad and hit save. Open up your newly altered str file. You'll know right away if you've messed up because it won't open if there's anything wrong. If you're having trouble, it might help to start with a few star systems instead of 1,000 to see where you're going wrong. But once you've got it right, you'll be able to see all the stars that we found with orbiting planets. You might notice that the map I'm showing in the video has what looks like a bunch of lasers pointing at the solar system. These lines represent the error ranges for the star system's distances. I figured I'd put something in to keep this from looking like it's just a random assortment of stars. I mean, how it looks doesn't matter, it's accurate, and an accurate star map is going to look like a random assortment of stars. There are some features of the star map that are worthy of note. For one, generally speaking, the map gets increasingly denser as you get closer to the center, which is where we're located. This is no accident, as it turns out that it's easier to spot planets orbiting stars that are closer to where you're located. In our case, that's the solar system. An exception to this tendency is this column, right here. If you look closely or increase the text size, you'll see that all of the stars in this column are named Kepler or Koi. This is because their planets were found with the Kepler Space Telescope, which was a telescope that operated in space from 2009 to 2018 and looked for Earth-like planets around other stars in a narrow segment of the sky using what's called photometry, or detecting planets by measuring the dimming of a star's light when a planet transits the star. Many of the stars in this column here are from one telescope over a period of less than 10 years, looking at 1/400th of the sky for planets with orbits that just happen to allow them to transit in front of their parent star. And these are just the main sequence stars, and the telescope malfunctioned halfway through that 10-year period, after which they only looked at smaller, dimmer stars. In that time, the telescope helped astronomers find 2,600 planets, which is more than half of the total number of exoplanets we've found so far. I suspect we have a lot more planets to find. So, that's how you make your very own 3D star map with no special training whatsoever. You just need Spreadsheet software, an ad hoc program abandoned in the 90s, and information readily available on the internet. Speaking of information on the internet, the video description has all of the resources that I've mentioned, as well as the main source for the trigonometric equations used in this video, which come from a 2003 article by Greg Scalise. Who's Greg Scalise? The world may never know. So now that you've made your own accurate star map, leave some comments below about how much bigger your brain has become after learning so much from this video. Or you can let everyone know how dumb you are with troubleshooting questions. Don't think I won't answer your questions. So thanks for watching, and hit that bell or follow me on Facebook for the next time I release a video on something.